Greetings, I'm Squared here, and today we're going to talk about simplifying radicals. So we want to make sure that we understand this terminology, this little thing right here. Sometimes people call it a radical. It's called a radical sign. This little number up here is called an index, and what's inside or underneath the radical sign is called the radicand. Now you won't see an index unless it's different than 2. A square root, we don't put a 2 up there. You can, but we don't. We just call it a square root. If it's a cubed root, we put a little 3. It's a fourth root, we put a little 4. And so on. So the index changes, but if you don't see an index, you got to know it's always 2. So we're going to talk about simplifying radicals. We're really only going to talk about the first rule for simplifying radicals. There are 3 rules, but we're not going to get into fractions or denominators. So we're just going to talk about this one. The first one, no perfect squares as factors in the radicand. That means this radicand cannot have any factors that are perfect squares. If there are perfect square factors, then you need to get them out. Take the square root of them. I really like to have a list if I don't have these memorized beside me so that I can notice perfect squares, because basically anytime I see any of these numbers inside as a factor, I know that it's not simplified. So you definitely want to have one of those by you, or maybe you have them memorized. Okay, so we're going to learn something called the birthday cake method, and there are other methods, but I find this is kind of like foolproof. So we're going to simplify, again, no perfect squares as factors. Remember, factors just means 2 things that are multiplied. So remember back in the day when you did a little factor tree, we're going to kind of do that, but a little backwards. So we're going to start with 80. We're going to go down here with 80. And we're going to, this is a division sign, not a square root sign, okay? I'm going to divide 80 by multiple numbers until I get a 1. And that 1's going to be my birthday candle. When I get my birthday candle, I'm all done. So what I notice is that it's even. I always start, if it's even, with 2. So I say, what's 80 divided by 2? It's 40, and I put it up here. But then I continue. We'll switch colors so you can see. I'll just do it on the first one. I continue. Is it still even? Yes. Basically, I'm getting the prime factorization of the number that I'm trying to take the square root of. So 2 went into 80 40 times, 2 goes into 40 20 times, 2 still goes into 20, it goes in 10 times, 2 still goes into 10, it goes in 5 times. Now 2 doesn't go into 5 anymore, but something still does. Remember, I don't stop until I get a 1. So I go to my next, I use my prime numbers always. So here's my first few prime numbers, etc., etc. So 2 didn't work, so now I check 3. 3 doesn't work. Now I check 5. 5 works. 5 goes into 5 1 time. Birthday candle. Okay? That means all of these are what multiply to get 80. 2 times 2 times 2 times 2 times 5. So all of that multiplies to get 80. That's really important that you understand all these outside numbers are what you get, what you multiply to get 80. So then I look for pairs, because this would be a 4 and this would be a 4, right? So I could change my 80 to 4 times 4 times 5. And then I can take the square root of 4 times 4 times 5. Remember, I'm looking for factors that are perfect squares. So anytime I find 2 of the same, that becomes a perfect square. 4 is a perfect square. So it's kind of like taking the square root of each factor. What's the square root of 4? It's 2. So the 2 comes on the outside because I just took the square root of it. Be careful with that. A lot of people want to put a square root sign over the 2 after you already took the square root. The square root of 4 is not the square root of 2. The square root of 4 is plain old 2. So it's a 2. What's the square root of this 4? Still a 2. They were multiplied inside. They don't magically get to be not multiplied on the outside. We're still being multiplied. So the square root of 4 is 2. The square root of that 4 is 2. The square root of 5? There's no square root of 5 that's perfect. It's not a perfect square, so it stays in. So my final answer, I multiply these 2, and I leave what I couldn't take the square root of inside. Now, if you want to have a double check, one thing that's nice is you can actually find the square root of 80 in your calculator. Say it's 8.944, da 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 da. You can also take this, 4 square roots of 5, 4 times the square root of 5, and see if you get the same thing. Yeah, you do. So that's kind of a double check. It doesn't mean it's completely simplified, but it's nice that it's a double check. Okay, I'm not going to use different color pens. I'm just going to go for it. So again, I put my 48 down. I'm finding all the prime factors that multiply together. I'm finding the prime factorization. So I start with 2. 2 goes into there 24 times. 2 goes into 24 12 times. 2 goes into 12 6 times. 2 goes into 6 3 times. 2 doesn't go into that anymore, but 3 does. 1 time. Birthday candle, all done. See kind of how I made the birthday cake? So now I have 1 set of 2, 1 set of 2, right? So now I have 4 times 4 times 3 is the same thing as the square root of 48. Well, that square root of 4 is 2, and that square root of 4 is 2. I cannot take the square root of 3 and get something that's an integer, so it stays inside, and my answer is 4 square roots of 3. That is the simplified version of the square root of 48. All right, moving on. Notice there's a number out front. That's okay. It just means at the end we're going to multiply it by whatever we get. So we got 18. 2 goes into 18 9 times. 2 doesn't go into 9, but 3 does. 3 goes in 3 times. 3 goes into 3 1 time. Birthday candle means I'm done. Got 2 3s. That means I've got a 9 times 2. Well, what is the square root of 9? It's 3. Notice there's already something there, so I have to do 3 times 4 when I take it out. The 2 stays in, because I cannot take the square root of that and make it something pretty. So my answer is 12 square roots of 2. Okay, so here we go. 63. 63. Well, 2 doesn't go into that, but 3 does. 3 goes into there 21 times. 3 also goes into 21 7 times. 7 goes into 7 1 time. I have 2 3s. So here's a little shortcut for you. If you have 2 3s, did you notice that that's the square root of 9, which is just 3? So if I have 2 3, it's kind of like taking the square root of it is 1 3, so it's just on the outside. Makes it a little bit easier if you don't want to do that other step. Okay, 5 times the square root of what? Okay, 60. 60. 2 goes into 60 30 times. 2 goes into 30 15 times. 2 doesn't go into 15. 3 goes into 15 5 times. And 5 finally goes into 15 1 time. Birth candle, I'm all done. There's my 2s. That means 1 jumps out here. I don't have 2 3s, and I don't have 2 5s. That means they have to stay inside here. So I end up with 10 square roots of 15 as my answer, my simplified answer. All right, hopefully you're getting the hang of it. I just wanted to talk about variables for a minute, because those didn't have any variables in it. So when you look at this, I wanted you to kind of just look and see if you notice a pattern. So the square root of x squared is x. The square root of x to the 4th is x squared. But in between there's an x cubed, and it's x square root of x. What happens is when you have x cubed, you have an x squared times an x. And x squared is a perfect factor, and it equals x. So that's why the x comes out. So a little shortcut might be that if it's even and you're dealing with square roots, that if there's 2 of them, 1 comes out. If there's 4 of them, 2 comes out, because you have an x squared and an x squared. So if it's even, it's the shortcut kind of way to think about it is you're dividing that by 2, and actually this is the same thing as this. You learned that. Well, you were supposed to learn that already. But anyway, you might not remember it. So that's how you get that 6 divided by 2, because that's that 1/2 right there, which is the same thing as dividing by 2. And if you have an odd one, that means there's going to be 1 left in there when you deal with square roots. This is just about square roots, not cubed roots. The same pattern kind of applies, but it's a little bit different when you go to different indexes. But we're only dealing with square roots today. So if you have an odd number, you know you're going to have 1 left inside. If you have an even number, you know you're not. So let's do this one. We have an x to the 9. 9 is definitely odd. So I would change this into x to the 8th times x. That's still 9 x's. It's just that I moved that one over because I know I'm going to keep that one in. And I have 8 x's, and for every 2, 1 comes out. So x to the 8th, the square root of that is x to the 4th, but I've got to have 1 left. So there is my answer for x to the 9th. Now I have 2 variables, so I know I'm going to keep 1x in because it's odd, so it's x squared times x, and I know I'm not going to keep any y's in because that's even. So the square root of x squared is x. The square root of y to the 10th, remember we divide the 10 by 2 because there's 5 groups of y squareds. So then I have my x left. And then of course that's my answer. We combine them with numbers. So sometimes we have numbers and variables together. So we have a -3. We have a 50. Now here's another way to do it. I don't always use the birthday cake method because sometimes I can just see it. I'm like, oh, 50. That's 2 times 25. And I know the square root of 25 is 5. So I don't need to go 5 times 5. Do the little birthday cake method. And then I have x to the 10th times x, which is x to the 11th. So then I'm like, these two can come out because I can take the square root of that. Those are perfect squares. The square root of that is 5. The square root of that is x to the 5th. And then that was out front, so I'm still going to have to multiply it by that. And then what's left is this 2 and that x, so I just leave a 2x inside. So when I clean this up a little bit, I just multiply my like terms, -15 x to the 5th times 2x, and that is my answer. So that is simplifying radical expressions. Good luck with that. M squared signing out.